Hello, my name is Dr. Jared Ellinger, and I worked under Dr. Jonathan Rogers in the Intelligent Robotics and Emergent Automation Lab at Georgia Tech. Thank you for coming to my talk today on the causation entropy method for covariate selection in dynamic models. To give an overview of this presentation, I'll begin with the problem motivation. I'll then provide some background on information theory and provide the definition of the causation entropy matrix, or CEM. And then I will provide the results from this work, which is a comparison of the CEM with current state-of-the-art covariate selection techniques. To begin with some problem motivation, system models are critical in many engineering problems. Often we have access to or can generate sample input-output data from a system, and system identification is the process of using this input-output data for model generation. There are several classes of system identification problem, but in this work, we focus on gray box modeling, which is a problem where we have some knowledge of the model structure and parameters. We focus on one subset of the gray box model, which is the problem of the unknown parameters, which considers the case where a model structure is either known or assumed, and the goal is to identify the system parameters to complete the model. In order to do this, model optimization is typically used. For linear systems, this is a convex optimization problem and will converge to the global extrema. However, in the case of nonlinear systems, it's more complicated. Given a nonlinear system is represented here, where theta is a parameter and f is a function of both the state and time, we can use maximum likelihood estimation for the selection of parameters theta. In order to do this model optimization, we often use maximum likelihood estimation, which there are many different types of, but a common method used is output error minimization, where we attempt to match a possible model output to that of the observed data. Output error minimization, like many other techniques, requires a local optimization routine, which can cause us to converge to the wrong extrema if the problem is non-convex, which is very common with nonlinear systems. The risk of converging to the wrong extrema is that it leads to poor generalization to unseen data. It's a problem that arises where the training error can be very low, but it doesn't generalize well to unseen data, as either too many parameters are used or an incorrect set of parameters is identified from the training data, which causes the training error to appear low. However, when used over new data, the performance is unpredictable. This problem is what's known as overfitting. To address this problem of overfitting, many attempt covariate selection, or as it's known in some fields, feature identification, to identify and remove unnecessary parameters before running the optimization to limit the problems due to overfitting. I'll now provide some background on information theory, which begins with the Shannon entropy H, which is a measure of uncertainty of a random variable. Additionally, we can define a conditional entropy H of y given x that's very similar in nature to that of the Shannon entropy. It measures the uncertainty of y given knowledge of x. With these definitions, we can define the causation entropy. Read here is the causation entropy of z to x given x and y. It measures the information that z provides to x in addition to the information included in x and y. We can write it more compactly as the causation entropy of z to x given s, where s is a multivariate random variable of potential functions. As a note, the causation entropy must be non-negative. Zero causation entropy implies that z provides no additional information to x beyond what is in s. With this, we can define a causation entropy matrix, which is a specifically formulated set of causation entropies, as shown here. Each entry provides the amount of information that a parameter's function provides the next time step beyond what's included in all functions considered. It's easiest to understand this construction if we directly compare it to the parameter matrix of thetas in the state space representation. If we consider the 1,1 entry in the parameter matrix, what it represents is the impact that F1 has on the next time step of state 1 beyond the effects of all the other functions considered. If theta is non-zero, if theta11 is non-zero, it means that F1 has an impact that can't be modeled by the other functions in the system. The 1,1 entry in the causation entropy matrix observes a similar quantity. It is the amount of information that F1 provides to X1 given all the other functions considered in the system. And the only way this can be zero is if theta11 is equal to 0. Thus, we can use the CEM for covariate selection by identifying entries in the causation entropy matrix and removing them from the optimization routine. I'll now give a comparison to some current state-of-the-art techniques. Namely, we focus on embedded covariate selection techniques, which seek to combine covariate selection and optimization into one task. Recently, there's been a lot of work using lasso and elastic nets as two leading methods to this end. They work to use approximations to the L0 norm, which encourage sparse results, by using the L1 norm and L1 and L2 norm, respectively, for lasso and elastic net, as using the L0 norm directly is computationally problematic, as it's not a true norm. Two systems were studied in this work, one linear and one nonlinear. The linear system is shown here below, and we can see that there are many zeros throughout the model that risk overfitting if the parameters are identified through the optimization routine as being non-zero. Additionally, we had a classical van der Pol oscillator that was discretized through a first order finite different approximation. Additionally, we added a set of parameters that are zero, but were entered into the optimization routine to allow to better visualize the effects of overfitting by including extra unnecessary parameters. To begin, we ran a study using no noise and compared the the covariate selection accuracy, which is the accuracy at identifying the model structure or identifying which parameters are needed and not needed for various data lengths of the training data. 50 simulations were averaged. As we can see in both the linear system figure on the left and extended van der Pol system on the right, the CEM performed better than both lasso and elastic net. Additionally, it's particularly visible that in the case of the nonlinear system, the CEM was able to converge to its best estimate of the system with access to far less training data than either lasso or elastic net. On these plots, the red error bars represent one standard deviation of this covariate selection accuracy seen, with the blue error bars corresponding to the minimal and maximal error seen throughout the study. In practicality, there likely won't be no noise in true systems. So next we decided to study the case of noise being included in the system. Measurement noise was drawn from a standard normal distribution and then multiplied by scalar multipliers to impact the magnitude of the noise. The figure on the left is the same plot as shown previously, where in this case, the covariate selection accuracy is compared to the number of data points in the training data. And we can see that once the noise is non-zero, the CEM and lasso and elastic net techniques have very similar performance. However, their performance degrades in different manners. The figure on the right represents the fraction of zero entries in the identified model, or the number of zero entries identified over the total number of parameters. The green dashed line represents the true system's fraction of zero entries. What we can see is that as noise increases, the CEM becomes overly sparse, while lasso and elastic net become overly populated. To study the effects of these different methods of degradation, we considered two different cases. The first is short-term prediction, or the case where there is measurement update, similar to how a Kalman filter functions. We also checked long-term prediction, where there's no measurement update, which is similar to a model simulation or trajectory planning type application. We then ran the test for two different scenarios. The first, where the training and testing data sets overlap, or where essentially this is the case where the testing set was seen during training. And then we also tested the case where the training and testing data sets are distinct, or the case where the testing data was not seen during the training phase. And what we can see is that in the case of the training and testing data, when they overlapped, as shown by the two figures on top, for short and long term, the CEM, lasso, and elastic net techniques all had very similar results. However, when we moved on to the case of the training data and testing data being distinct, we begin to see more of a difference. What we see is that in the case of short-term prediction, or the case where there is measurement update, the CEM has far better performance than lasso and elastic net. And the cause for this is that the CEM does not overfit the model and thus is able to more accurately represent the data over in cases that are different from what it was trained over. However, when we move on to the case of long-term prediction, we see a slightly different story. And in this case, lasso and elastic net actually have improved performance. And the reason for this is that in the case of long-term forecasting, we see a case develop where The causation entropy matrix, due to being overly sparse, is not able to actually represent the entire dynamics of the system. It goes for a reduced order model, which works well over short durations of time, but is less effective over over longer periods of time, due to the fact that it uses a simpler model. Thus, Lasso and ElasticNet were better able to represent the system for long-term forecasting. To tie up and conclude this presentation, the causation entry matrix provides a novel method for covariate selection. It provides improved covariate selection over Lasso and ElasticNet techniques that have become popular in the literature recently. And this is an important case, is this case of no noise provides the ceiling on performance. So should filtering or other techniques to limit the effects of noise be included, the CEM has greater potential than these methods. However, in the presence of unmitigated noise, the CEM will become overly sparse, while Lasso and ElasticNet will become overly populated. With the distinct training and testing data, the CEM performs better for short-term forecasting due to limiting the effects of overfitting, but worse for long-term forecasting, as its overly simplified model is simply missing too many parameters to entirely model the system. I'd like to thank everyone for coming to this presentation, and I now open the floor to questions.